Hey y'all, so today I wanted to make a quick video just explaining what KSP is. I've been getting a lot of questions in my office hours and after class about what KSP is, and this is my answer. So a lot of students, when I ask them what KSP is, they'll always answer, "Oh, it's the solubility constant," and then I ask them what that means, and they usually can't answer me. So I'm going to try to explain that now. And in order to do that, we have to understand what K in a more general sense is. So K is what we call the equilibrium constant. It's when you have a reaction like this, and it's at equilibrium, which means that's kind of like the ending point of the reaction. It's where it kind of stops. It's that point. Now, in order to quantify that, we have K equal to a ratio of the products divided by the reactants, okay? That way we can see how far the reaction goes. If it goes all the way and makes all product and consumes all of the reactants, then this number is going to be really, really big, right? Because if it's really, really big, products, reactants, then that means we have a lot of products and almost no reactants left, which means it's going to be quite a large number. On the other hand, if the reaction doesn't go at all, right? We throw some kind of salt into water and almost none of it dissolves, then we formed very, 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 very little product, maybe like one or two ionic units separate into ions, and the rest of it stays as a solid, then this number is going to be pretty much basically close to zero. So what K basically gives you then is a range. 0 to infinity, reactants, products. What the K value is, it tells you where along this range this particular reaction goes. Okay? But more specifically, KSP, what we're talking about here, is the K or equilibrium constant for dissociation reaction. So a reaction like this, right? You might have like NaCl going to Na plus and Cl minus, right? That's AA going to B and C, okay? Now, where this comes into play on the exams are when you are given something called Q, okay? So if K is how far the reaction goes at equilibrium, Q is the instantaneous where is the reaction right now, okay? So Q is where it is right now. So it follows the same pattern but instead of being the concentrations at equilibrium or at the end, it's the concentrations at the current moment or at the moment of interest. So going back to this whole number line thing, let's say we have a reaction where K is equal to 1.5, right? That's where the reaction wants to end up. It wants to have a 1.5 ratio of reactants to products, okay? But let's say that right now I tell you, by giving you concentrations of stuff, and you calculate out that Q is right now is going to be equal to, let's say, 7, okay? What is that saying? Well, that's saying that right now I have a lot more products than I want. I'm really favoring this side, but in reality, I want to be somewhere towards the left. I always want to end up at equilibrium. That means that I've produced way too many products, or I started off with way too many products. I need to shift to the left or shift to the reactant side. What does that mean then? Well, if these are ions, and this is the salt, that means I'm going to get rid of ions by making more salts, aka making a precipitate, okay? What happens then if we do the opposite case then? Let's say K is still 1.5. What if I start off with a Q that's, I don't know, like 0.5? Well, that means that right now I have a lot of product, or a lot of reactant, a lot of reactant, and I want to end up here, like we said before. So how do I do that? I have to shift to the right, or shift towards the product side, and get rid of this salt, aka dissolve it, and make more ions, okay? So that's what we mean when we say that Ksp is the solubility equilibrium constant, and how Q will shift to meet K, and how you know whether or not something precipitates or not.